Section 1 starts off with a pretty basic question, and that question is, what is statistics? So, just to get an example here to get started, let's consider this case here where we have got some numbers here. These represent the annual wages in thousands of employees at this place called S-Mart. So you can see you got some employees making $30,000 a year, a couple making $40,000, one making $150,000. And let's say these employees go on strike. You've got the smallest union in the world, but they go on strike over wages, and both the union rep and the business owner are asked by the local news media what the average pay is at S-Mart. You've got a couple responses. The union rep says the average pay is $30,000 per year. The business owner says the average pay is $50,000 per year. So these sound completely different. So the question is someone lying? So what do you think? Is someone lying? Are they both lying? Can they both be telling the truth and get totally different numbers like that? Well, what some of you may be thinking is that maybe they're talking about different averages. So there's a word we have to be kind of careful about. Average. This word average can mean a lot of things. There really are about 14 different ways to calculate an average, and they could all be used here. Now there's 3 of them that you typically learn about in school. They, at some point in high school or college, you'll hear about ways of taking averages, and the 3 that come up, they always start with an M. What do you think they are? Mean, median, mode, right? You always hear about those, the mean, the median, and the mode. Well, 2 of those are used all the time. That's the mean and the median. The mode really is hardly ever used, but it always comes up. So we'll look at these in more detail later on, but just to get an idea, can you think about using the mean, median, or mode? How could you come up with an average of 30,000 using these numbers? And that would allow you to say the average pay is 30,000 a year. Well, if you think about the mean, median, and the mode. Okay, mode, that's one that comes up the most, right? So if we look at these numbers here, the mode here is 30, right? $30,000 a year, that's the mode. Again, the mode is not really used a lot, but if you were going to use it here, you could. I mean, the mode is 30,000, so typically that one's not used. But what about the median? Do you remember what the median is? If you're, you write these down here. So, like I said, we will talk about these in a lot more detail later. But there's the mean, the median, and the mode. We actually will study 5 different ways to calculate averages. These are 3 of them. And we look at weighted means and trimmed means also later. But there's about 12 or 14 different ways to calculate averages, like I said. But the 2 that you see the most are the mean and the median. And there are times when you should and shouldn't use both of these. So for right now, the median, that is where if you line up all the numbers in a row, the median is right in the middle. These are lined up, right? Lined up in a row, meaning from smallest to largest. So they're lined up from smallest to largest. So this is the number in the middle. So the mode here, the median here is 30,000. So if you say the average pay is 30,000 a year, it's technically true if you use the median. Now, I'll tell you that typically when money is involved, you do use the median for reasons that we'll see later. But the median is typically not affected by outliers where the mean is. So the mean Many of you will remember when you find the mean, you add up all the numbers and divide by how many there are. And if you add up all of these numbers and divide by 1, 2, 3, 4, 5, 6, 7, divide by 7, you end up getting this number 50, which represents 50,000. So that number is the mean. So both of these statements are technically true, right? They're both technically true. So nobody is lying, but you could say maybe one of them is a better number in this case. Like you could say, well, maybe, although no one is lying, it could be a little misleading to say the average pays $50,000 a year, because really only one person makes that much. So if we're using average to mean like a typical number, it's not a very good number to represent a typical number in this case. Although technically it is true, the mean pay is $50,000 a year, so you could say the average pay is $50,000 a year. But this number would be better in this case because it represents more of like a typical number here. So they're both technically true. So nobody's lying here. There would be times when you want to use the median, sometimes when you want to use the mean. But we just have to be aware that if somebody's trying to convince you of an idea or convince you to buy a product, you have to really pay attention to what you're being told. You could be being told something that's absolutely true, but it's absolutely misleading. And this happens constantly. It happens daily on the news. It happens all the time with politicians because they're trying to convince you of an idea. So we just have to be aware of it. And it's even worse now because it used to be, especially in politics, you just had to be sort of clever in how you spoke so you could be saying things that were technically true but maybe supported your cause. But now it seems you can just say anything you want. It's kind of unusual. We're in unusual times now. But anyway, this is a really easy idea where you can see these numbers are totally different and they're both true statements. So we just have to be careful. We have to understand statistics so that we have a good understanding of what's happening in the world and we're not easily misled. As an example of this, I'm looking at an article that was published in mlive.com in February of 2021, and the title is this. It says, here's a quote, "Average Michigander had nearly 1,000 alcoholic drinks in 2020. That's a lot," end quote. So it mentions the average Michigander had nearly 1,000 alcoholic drinks in 2020. That is a lot of drinks. But here's the problem. If you look at the article, you'll notice it says a study by drugabuse.com. Okay, now drugabuse.com is an advocacy group or special interest group. So it doesn't mean that it's going to be bad data. It just means it's a little bit of a red flag, right? It's like this is a special interest group. Again, it doesn't mean that it was bad data, but it's just something to be aware of. But then when you look at what the article says, it says drugabuse.com surveyed 3,000 drinkers, not 3,000 Michiganders, 3,000 drinkers. So the person who came up with the title for this article had a very bad understanding of statistics. Surveying 3,000 Michiganders and 3,000 drinkers is not the same thing. That would be like me surveying only hunters who shot a deer and then saying something like, average Michigander killed 2 deer in 2020. That's a lot. So it's just an example. We have to be able to understand statistics to make sense of things. So because of that, there's a debate that's starting in schools. And there's maybe a transition coming. So in most schools right now, the highest math class you can take is calculus, and there are classes that will lead you up there. You'll have algebra and then trig and then maybe pre-calculus and then calculus. Well, there's a push right now to switch that so that statistics is the top class. And the reason is because of the fact that in the world we live in today with big data, tons of data, There's real-time analysis, there's risk and reward that we have to be aware of, and statistics better handles that. So for the average person, the thinking is maybe we should have this be the class that everybody shoots for. And this one will still be there because calculus, we need calculus for the STEM fields and for engineering and things like that. So this will still be there, but we kind of like shift the focus so we're aiming the majority of people towards statistics. So it's sort of a push. So these pushes take a while to happen, but it may happen. It may happen. Maybe when your kids are in school, statistics will be the top class. And I've got a video here from Arthur Benjamin. It's a TED Talk, but it's a real short one, and he makes a pretty good case. So I'm going to play this for you guys so you can see what you think about it.
Well, if President Obama invited me to be the next czar of mathematics, then I would have a suggestion for him that I think would vastly improve the mathematics education in this country. And it would be easy to implement and inexpensive. The mathematics curriculum that we have is based on a foundation of arithmetic and algebra, and everything we learn after that is building up towards one subject. And at the top of that pyramid, it's calculus. And I'm here to say that I think that that is the wrong summit of the pyramid. That the correct summit that all of our students, every high school graduate should know, should be statistics, probability, and statistics. I mean, don't get me wrong, calculus is an important subject. It's one of the great products of the human mind. The laws of nature are written in the language of calculus. And every student who studies math, science, engineering, economics, they should definitely learn calculus by the end of their freshman year of college. But I'm here to say, as a professor of mathematics, that very few people actually use calculus in a conscious, meaningful way in their day-to-day lives. On the other hand, statistics, that's a subject that you could and should use on a daily basis, right? It's risk, it's reward, it's randomness, it's understanding data. I think if our students, if our high school students, if all of the American citizens knew about probability and statistics, we wouldn't be in the economic mess that we're in today. Not only that, if it's taught properly, it can be a lot of fun. I mean, probability and statistics, it's the mathematics of games and gambling. It's analyzing trends. It's predicting the future. Look, the world has changed from analog to digital. And it's time for our mathematics curriculum to change from analog to digital, from the more classical continuous mathematics to the more modern discrete mathematics, the mathematics of uncertainty, of randomness, of data, in that being probability and statistics. In summary, instead of our students learning about the techniques of calculus, I think it would be far more significant if all of them knew what 2 standard deviations from the mean means, and I mean it. Thank you very much.
So in the coming years, we may see that transition start to happen in the schools. But one more thing we should talk about before we really get started here. Just want to give you a little bit of background about statistics. So to compare statistics to some other areas of math you've heard of, let's compare it to, say, geometry. And I'm not going to ask you about this on a test or a quiz. I just want you to have some idea of what we're dealing with here, because statistics is very new when you compare it to these other branches of math. So geometry, we can trace this back to Egypt. And they use what we would call practical geometry. This is as far back as 3000 BC. So, 5,000 years ago, there was an understanding of all the basic shapes and areas and volumes, geometric figures that were used for determining boundaries of properties and things like that. So this is 3000 BC, and it has not changed. There's have been no changes in this sort of geometry. The area of a square is still x squared. So if x is the length of a side, then the Greeks, who could talk about Euclidean geometry. And this was, there was a book published in about 300 BC. 300 BC, there's a book called The Elements, which you may have heard of. The Elements was published by Euclid, and it has been published routinely ever since then. There's been over 1,000 editions. And in fact, there's only one book that's been published more often than Euclid. Only one book on the planet. You know which one that is? It would be the Bible. It's the only one with more editions than the Elements. In fact, if you studied math up until around the year 1900, you would have read the Elements. That would have been part of your training in studying mathematics. And since then, there have been some other, many other geometry textbooks published, and a lot of them even that you studied in high school. A lot of you took 10th grade geometry, and that was still based on the elements, 2-column proofs and things like that. So the point is, though, that if you go way back to these times, we are still using these same principles of geometry. It has not changed. And there's been other sorts of geometry. So that what we're talking about basically here is Euclidean geometry. And there are non-Euclidean geometries and different topologies that are studied. But the basic Euclidean geometry has not changed. So the book you studied in high school wouldn't have changed a whole lot from this one back here, 300 BC. So it's geometry is well established, not any big changes. Even calculus. I teach calculus, and the book that we use has theorems that haven't really changed too much in the past 300 years or so. So even calculus has had, at least at the basic level, there have been not too many changes. It sort of got all pieced together roughly 300 years ago or so. And the theorems that we look at are the same theorems you would have seen in a book 100 years ago. Now, all of that is completely different when it comes to statistics. Statistics is a much newer subject, and it's still changing. There are things that are not settled yet in statistics. So when I was a student, I took the same class that you're taking right now. This is a first-year statistics class, and I even had the same author in the textbook I had, but I had the second edition, where now we have the 12th edition. And the things that we did in statistics in the second edition are different because we can use better techniques now because we have graphing calculators. And without a graphing calculator, you're forced to use tables. So they lack a certain amount of precision that allows you to do more. That now we can do more with the graphing calculator. So certain techniques are changed. Because if you don't have this graphing calculator, you have to do your calculations differently. So sometimes you need an entirely different technique. So it's changing. So just to give you some background here, see how new this is. Again, I'm not going to ask you about this. It's just so we can see where we're at. I want you to, the thing I need you to understand about statistics is it's new, it's fluid, it's changing. And it's changing even right now. There are disagreements. There are certain things that are not dialed in. And so in different fields, you do things a little differently. So it's something you'll notice. I just want you to be aware of it. So probability. it wasn't studied a whole lot until about the 1650s, and even then, it was only certain things were studied, and it was driven by gambling. So they're professional gamblers who started asking mathematicians questions about dice games and card games. And that was really the driving force for the subject of probability. And there wasn't a whole lot of advancement for a while other than just answering particular questions about card games and dice games. So modern statistics this started to be developed in the late 1800s. Like a lot of it was like around in the 1890s, so not that long ago. And to really understand statistics, you have to first understand probability. So when this started happening, then there was some more discussion of probability, and it went away from just the ad hoc methods developed for gambling, but into more general methods that could be used in statistics. And then there's some advancement here. And then the undergrad stats that we study, and pretty much that everybody studies in college, these were mostly developed in the 1930s. So again, it's fairly new. That's one thing. So this is the statistics that our book covers, and that pretty much any stats book that you look at would cover. Now, the 1930s, think about computer technology in the 1930s. Not so good, right? So a lot of the techniques that were developed were not the best techniques, but they were the best practical techniques. If you don't have a computer, there's certain techniques that you're just not going to be able to do. So because of that, as computers developed more, some of these methods changed, and they're still changing. As we developed more counting methods where you don't have to use just brute force counting, but where you can use computers to help you, then the techniques change, and they are still changing. So that's where we're at. So these were developed mostly in the 1930s. And they're still changing, so just keep in mind there will be changes. If your kids take statistics and you help them with their homework, assuming you remember everything that you learned this semester, I can promise you there will be changes, because they're just, like I said, there are techniques that are still being debated and still not quite established yet. So I've got this life table here. And this is a very depressing looking life table. This is from 1662, and John Grant published the book. And a lot of historians credit this as being the beginning of statistics. So this is 1662, and John Grant used some basic statistical methods to estimate birth rate, death rate, and the population of London. So to see what this means, this is pretty depressing. Like I said, if you count up these numbers right here, you get to 60. So what that means is, of 100 people who were born in this era, 60 of them died before the age of 16. So they didn't have a lot of the things that we have right now. Access to clean water, which we pretty much take for granted, that's a pretty modern miracle, actually. So access to clean water was very difficult to come by, and that makes a big difference in life expectancy. Also, there were things antibiotics didn't really come out until the late 1950s. Penicillin. So if you had a plague that could have been a bacterial plague, there was just nothing to fight it. So no antibiotics, vaccines. There used to be just some terrible childhood killers like smallpox, polio, measles, mumps, rubella. Parents for thousands of years worried about these kind of things, and vaccines pretty much took them away. So that's why our life tables are not so depressing anymore. So look at this. For every 100 births, approximately one person made it to the grand age of 76. And this is pretty much the history of the earth until modern times. It was always very difficult to be a human, and most people estimate the life expectancy for most of the time on earth for humans was somewhere between 30 and 35, and it was usually a pretty rough life. Now, it doesn't mean there weren't old people. It just means that it was really fairly difficult to survive childhood, as you can see here. 60 people out of 100 would be dead before 100, or before 16. So we're going to look at a modern life table, which is much happier. So in modern times, the life table that we have is from 2008, and in those times, 66 out of 100 people, which is still roughly the same today. So today, close to 70 people out of 100 can expect to make it to the age of 76. So life expectancy, just to put some things in perspective, life expectancy in the United States in 1900, life expectancy was roughly 47 years. Again, it doesn't mean there weren't old people. It just means that a lot of people died young because of a lot of terrible diseases that we had to deal with. And again, clean water, things like that. But now the life expectancy is roughly 79 or so. So what we're going to do is see a modern life table, which we've got right below here. And the way this works, really what you need to do is look at your age over on the left. So you find your age over here, and then if you follow over here, this is your expected, your average, meaning the mean in this case, amount of years you should expect to live if you are in this age group. So find your number, and then I have some good news for half of you and some bad news for half of you. So if you look over here, so let's say you're 21. So you look over here, so don't read it like, what? I'm only going to live to 58? That's not what it means. It means you've got 58 more years left at this point. Okay, so that's average. So once you find that, you get good news and bad news. Okay. Ladies, good news for you. This is a composite table, so it means it's the ages of men and women. And women generally live longer. So ladies, if you look at your number, add 1 or 2 years onto your number. And then for the guys, bad news. When you look at your number, take away 1 or 2 years. But even with that, living in modern times is a much happier looking life table. Okay, so that's just wanted to get us away from that sad life table and look at a more modern one. And what we will do at this point, finally what you've been waiting for, we will actually take a look at the section 1.1. I just wanted to give you guys an understanding of where statistics is. It's new, it's changing. There are a lot of disagreements among statisticians and researchers about how to do things. But we're going to look at the basic first year stats class. So the first couple of chapters, unfortunately, there's just a lot of definitions, and we just have to get through these. Okay, so statistics is more interesting than it's going to seem at first because we're going to go through all these definitions. So just kind of bear with me a little bit, and let's get through these. So here is a definition that our authors use in our textbook, and they define statistics this way. They define it as a study of how to collect, organize, analyze, and interpret numerical information from data. And why do we study statistics? This is one reason you could say, to make more effective decisions. Okay, and there are a couple branches of statistics that we're going to study, and pretty much everybody studies these. There are descriptive statistics. Okay, so descriptive statistics, this is what we look at first, chapters 2, 3, and 9. And this involves methods of organizing, picturing, and summarizing. Information from samples or populations. And descriptive statistics is easier for sure. It's definitely easier. To me, it seems less interesting, but it's making graphs and charts, talking about mean, median, and mode. And it's easier to do, so it's typically covered first in the stats class. So descriptive statistics, we're describing a data set. The more interesting part of statistics, and definitely a little more challenging, is inferential statistics. And this is really why we study statistics. This is starting in chapter 4. And this involves methods of using information from a sample to draw conclusions about the population. So this is where you look at a sample. All you have is a sample of data, and then you try to infer information about the population that the sample came from. Okay, so we'll start off with descriptive. We'll move to inferential statistics. And this class starts off pretty basic, so be careful about that. It starts off with descriptive statistics, which many of you are familiar with just from previous classes and just from being alive on the planet, and you run into some of this stuff. So students sometimes think, oh, this class is pretty easy. I don't really need to do the homework or do anything. Then all of a sudden you get into chapter 4, and there's permutations and combinations, and everything changes. So it's best just to get a good habit. Stay right on top of the homework, even if it's stuff that seems familiar. Stay right on top of it in these chapters, and then we'll move on to inferential statistics, and you won't really notice a big change. Okay, so in using statistics, we typically know only the results of a sample. The central problem is to describe the sample. Describe the sample, which is that descriptive statistics we just talked about, and to draw conclusions about the population based on the sample results. And that is inferential statistics. So it's just a little paragraph summarizing the two that we just mentioned. And sometimes people say, why wouldn't you just use the entire population? We'll talk about that, but typically you either can't, or it's extremely expensive or difficult, so we will use a sample. We'll look at the sample and try to infer things about the population. But before we do that, we have to gather data. So in order to gather data, we need to be able to know what we're talking about here. So the individual, this is the people or objects included in the study. Those are the individuals. So if you are studying, let's say you want to figure out the average age or the mean age of a GRCC student, well, the individuals would be all the GRCC students, right? Those are the individuals. Then the variable, this is a characteristic of the individual to be measured counted or observed. It's basically the thing that we're going to measure. So if we were trying to figure out the average age or the mean age of GRCC students, the individuals would be the students, the variables would be the students' ages, right? That's the thing that we'd be measuring. Okay, so as an example, let's see what we've got here. So we'll find out why later, but often if you are studying human populations, you want to divide them by gender. So you have either all males or all females. We'll see why later, but for this example, let's say we've got some individuals and they are female GRCC students, and here are some possible variables. And remember, these could be pretty much anything that you can measure or count. So variables could be the height of individuals, could be the weight, could be the age, could be the nationality, and it could be the eye color. Okay, and variables can be quantitative or qualitative. Quantitative or qualitative. And we have to know because they require different sorts of mathematics, so we need to know which one we're using. So a quantitative variable, this is one that has a value or numerical measurement for which operations such as addition or averaging make sense. And when you think of averaging, think of the mean, not the mode. Think of, would it make sense to say what is the mean? If it does, then it'd be a quantitative variable. So if you're trying to figure out the average age of a student's car, you could definitely find the mean age of a car, right? What about the mean make of a car or the mean color of a car? Those wouldn't make sense, right? So they wouldn't be a quantitative variable. So if you have a numerical measurement and taking an average would make sense, then you've got a quantitative variable. Okay, qualitative variable, which our book will use this phrase qualitative variable, but many other books will call it a categorical variable. Okay, so qualitative or categorical means the same thing. A qualitative variable, this describes an individual by placing the individual into a category or group, such as male or female. Okay, so for us, we've got quantitative and qualitative variables. And let's see, we've got a little note here. And the note says this. The note says, later we will see that quantitative variables are either discrete or continuous. Okay, you guys still with me? It seems a little strange for me, the online portion, because I can't see you guys. I can't see if I'm losing you. I can't throw in any of my horrible jokes to keep you awake. So try to do what you can to stay awake. It's not going to be. It's harder to hold your attention when we're in this sort of environment online, but guess we'll have to try to make the best of it. So, okay, in example 2 above, what we typically do in class is this is where you would get to meet who you're sitting with, which always makes things a little easier to keep us animated and keep active and awake and alert. So, can't really do it this time, but in example 2 above, what we want to do is write qualitative or quantitative next to each variable depending on which type of variable is shown. So up here we want to write, next to each one of these, we want to write either qualitative or quantitative for these variables right here. So in other words, looking at height, quantitative or qualitative? Quantitative, would it make sense to say what's the average height of a female GRCC student? And it would, right? Height would be just fine. So this would be a quantitative. So just take a second, press pause, and fill in the rest of them what you think, and then check back and let's see what you got. Okay, hopefully you pressed pause. Hope you're not just waiting for me to do it. So weight, average weight, that makes sense. That's quantitative also, right? Quantitative. Age, we could talk about the mean age. That would make sense. That's definitely quantitative. Nationality, could talk about the mean nationality. All right. That's not going to make sense. That's going to have to be qualitative. Right, that's a qualitative variable. And what about eye color? Mean eye color doesn't make any sense either, right? How could you add up like 17 brown-eyed students, 5 blue-eyed students, green-eyed students? It doesn't make any sense, right? So eye color is going to have to also be qualitative. Okay, so those are individuals. Those are the things that we're measuring, or the variables are the things that we're measuring from the individuals, and they can be quantitative or qualitative. Remember the other word for qualitative? Categorical, right? Our book uses qualitative. Many books use categorical. They mean the same. All right, let's look at a couple important definitions coming up here. So the population. This is a set of all measurements or observations of interest. And a sample is just a subset of the population. And we have to mention something here. Our textbook mentions both the individual and the variable when describing populations or samples. Another thing we need to know is that population and sample are usually not defined this way. So in our textbook, our author mentions that when you're talking about a population or a sample, they want to not only mention the individual, but also the variable, the thing we're measuring. Now, most textbooks or most statistical resources don't do that. Most of them just mention the individuals. So for definitions of population or sample, you can use whichever way you want. So you can do it more of a traditional way where you just mention the individuals when you're talking about population or samples, or you can do what our author does, which is to also add the variable. It's totally up to you how you want to do this. And I'll show you when we do this example 3 here, I'll show you what I mean in case you're not sure what I'm talking about. It's just a couple of different ways to do this, and either way it will be okay. So let's look at an example. So suppose you want to find the mean age of a GRCC student. So we take a sample and we interview 200 students. And so if the book asks us to define the sample in this situation, what we would write is, because the way our author does it, remember, when our author asks for the sample or the population, they want us to mention the individual and the variable. So the way our author in our book would define the sample in this case is, they would say the sample is the ages of 200 GRCC students. And then if we were asked to find the population, the way that our author would define population would be the ages of not 200 GRCC students, but all GRCC students. So if you look at what we've got here, the sample includes the variable, the thing we're measuring, and also the individuals, 200 GRCC students. Population does the same thing. We've got the variable, which is the age of the student, and the individual, all GRCC students. So basically we've got this. We've got, right here, we've got the variable. And then we've also got the individuals. These are the individuals. The variable, the individuals, and then the only difference between the sample and the population comes down to this right here. The sample, there's 200 GRCC students. The population, instead of 200, we have all GRCC students. Now again, like I mentioned before, a lot of statistical resources, if they were asked the same question, a lot of them would say the sample is 200 GRCC students. Notice they don't mention the variable, okay? I would say probably 8 out of 10 statistics books would define the sample in this case as 200 GRCC students. They would define the population as all GRCC students. Our particular book that we use, the Brace book, Brace and Brace were the authors, they include the variable with the sample and the population. And if there's a question about the sample or the population on a test or a quiz in our class, you can use either our author's variation here, which would be this and this for sample and population, or you can use a more traditional approach, which would be the sample is 200 GRCC students, population is all GRCC students. It's totally up to you. And this brings us to the data are versus data is controversy, which I did not know existed until I taught. And I had a take-home quiz one time, and there was a statement in the quiz, and I just worded it like the homework, said something about data are, and there was a student in the class who was not happy about that, and she handed in her take-home quiz, and I still remember she had that crossed out, and in all caps she said data is with an apostrophe at the end 3 times. Data is, data is, data is. I could almost hear her screaming this. So that's when I thought, well, maybe I better look into this and see what's happening. So it turns out that datum is a singular word that is hardly ever used, singular for data, and data is plural. In most math or science or technical books, you'll see the phrase data are. And when you're not in a technical area, you'll typically see the phrase data is. Usually in a technical area, people will want to be more consistent. So they will want to use data are because data is plural. It would sound better if there was an S on the end, datas are, but there's just not the word data. So oftentimes in technical areas, people are more concerned with consistency. So they're going to think, well, data is plural, so I'm going to say data are. In everyday talk, sometimes because it sounds a little awkward without the S, you'll hear data is. If you are on team data are, you can cite the APA style guide, which will support your claim. That suggests that we should use the phrase data are. But if you are on team data is, you also have a powerful ally on your side, which is, I believe, is the MLA, which is another one of the guides, and that one mentions that either is okay. So for us, either is okay. But you will notice our book is always going to say data are, as are most math and technical books. So either one in our class is okay, but my goal by the end of the class is to have all of you firmly on team data are. So we'll see how that goes. Related to populations and samples are a couple of terms here. A population parameter. In a population parameter, this is just a numerical measure, that describes some aspect of a population. An example of this would be the mean mu, Greek letter mu, is a population parameter. So this Greek letter mu, it means the mean. This Greek letter mu, it looks sort of like a cursive U, but it just means you took all of the data in the entire population, added them all up, and divided by how many there were, and you got the mean mu. So that is an example of a population parameter. We'll see other examples also. The sample statistic is a numerical measure that describes some aspect of a what? Can you guess? Of a sample. So as an example, the mean X bar is a sample statistic. So mean, see there's two different means here. The mean mu, which just means the mean of a population. Mean X bar is the mean of a sample. They both mean mean, but they're from different things. This is the mean of data that came from a sample. This is the mean of all the data in a population. The way to remember these, I think it's easy to think of population parameter, P and P, and then sample statistic, S and S. Because sometimes the book will just mention a parameter, or in class we may mention the word just parameter. So parameter goes with population, and a statistic that came from a sample. So population parameter, sample statistic. And there's a couple of notes here. So sample statistics, these may vary from sample to sample, whereas population parameters are fixed for a given population. So you could think of, if we took a sample, let's say we're going to try to figure out the average age of a GRCC student, and we took a sample of 200 students from the entire population of maybe 15,000 students. Well, if we took a sample mean of 200 students, then we took another sample of 200 other students, we shouldn't be shocked if they vary, right? We wouldn't expect them to all be the same. Each sample, every time we take a sample of size 200 from the entire population and we calculate the mean of the sample, we could get different numbers every time, right? So sample statistics may vary from sample to sample, but the population parameter, these are fixed for a given population. All right, by now I'm sure everyone is ready to try a problem. You're tired of me doing all the fun problems and you're ready to try one, I'm sure. This one is on page 11 of our book, and it is problem number 8. And the question is this. Well, it says, what is the average miles per gallon for all new hybrid small cars? Using Consumer Reports, a random sample of such vehicles gave an average of 35.7 miles per gallon. And question A is identify the variable. And then, is the variable quantitative or qualitative? And then finally, what is the implied population? So what you should do is try these, press pause, try these out, and then press play, and we'll see how you did. But you really should try them. You'll learn more if you try these on your own and think through and try to put all the pieces together than just to listen to me go through it. So press pause, try it, and then come on back. Okay, so hopefully you did that. And looking at the variable. So if you remember, the variable is a characteristic of the individual to be measured, counted, or observed. So the variable here is definitely going to be the mile per gallon rating, right? So the thing we're measuring is the mile per gallon rating. Next question, is the variable quantitative or qualitative? And quantitative sometimes is called numerical. Qualitative is sometimes called categorical. But in this case, it's definitely going to be quantitative because we could definitely talk about averages, right? We've got an average right here. So this is going to be a quantitative variable. And then finally, what is the implied population? So I'm going to write the implied population in the way that our authors would do it. In other words, I'm going to mention the variable. So in my answer to the population, I'm going to mention this variable, miles per gallon. So the way our authors would do this is they would say, what is the implied population? They would say it is the mile per gallon rating, right? Because remember, the way our book does it, it identifies the variable along with the individuals. So it'd be the miles per gallon rating for, since it's population, we want all, right? It's population, we want all of these, all new hybrid small cars. So this is the way our textbook would write the implied population. Remember I mentioned that there's another way to do this. It's more of a typical way you would see. The implied population would just be all new hybrid small cars. So if you wanted to call the population all new hybrid small cars, that would be just fine too. That's the way that most textbooks would define the population. Because again, remember, our textbook wants us to use the variable as part of the population or the sample. But for our class, you can do it either way. So I just wrote down the alternate answer there. And for us, you could write this for the implied population or this for the implied population. Whichever way you would like, they're both fine in this class. The last thing we look at in this section is the topic of levels of measurement. So we have done so far, we have categorized data as either quantitative or qualitative. Okay, quick quiz question. Do you remember the other word for qualitative that our book doesn't use but is pretty common? Categorical. All right. But there is another way to do this. Another way to classify data is according to one of 4 levels of measurement. These levels indicate the type of arithmetic that is appropriate for the data, such as ordering, like put the data in order, taking differences, or taking ratios. This classification was developed in the 1940s in psychology and has been widely criticized by scholars in other disciplines. So for a while I didn't teach levels of measurement. I stuck with either quantitative or qualitative because it has been just highly criticized. But I do see that it's still used quite a bit. So I think maybe it'd be better if we just covered this anyway. So what we'll do, so the data are categorized as nominal, ordinal, interval, or ratio. This is said to be the lowest level of data, and then it goes up. It goes up depending on what sort of math we can use with the data. So nominal is the lowest level, ratio is the highest level. It just goes in this order. So the nominal level of measurement applies to data that consists of names, labels, or categories. There are no implied criteria by which the data can be ordered from smallest to largest. So think of nominal basically as just names. So an example would be eye color. So there's really nothing, you can't really rank eye color. You could categorize eye color just by a name, right? Brown eyes, green eyes, blue eyes, something like that. Where it would never make sense to think of what's the average eye color, because how could you add up eye colors and divide by how many there are? And even if you do an artificial thing, like you could say, well, maybe I'll call brown eyes 1, green eyes 2, blue eyes 3. Those are an artificial numbering system because somebody else could number them differently. So if you get an average of 2.3, what does that even mean? So nominal level of measurement, just things we can put in the category, just a name. Think of nominal as a name, and that's all we can do with it. Ordinal, the ordinal level of measurement applies to data that can be arranged in order. So we can put things in order. However, differences between data values either cannot be determined or are meaningless. So an example here that we see a lot is something called the Likert scale. And these are pretty common. So a Likert scale could be something like 1 equals strongly disagree, 2 equals disagree, and so forth. So that they're arranged in order, but differences between the values may not make much sense. Like, is the difference between 2 and 3, between disagree and no opinion, is that difference the same as the difference between, say, agree and strongly agree? Scales are used quite often in surveys, and you'll receive them in emails nowadays pretty often. Or you could see something like maybe so let's say this is example 1. Example 2 could be something like, maybe there's a question about educational attainment. And they'll have things like, they want you to choose a number, maybe 0 equals less than high school, 1 equals some high school, 2 equals high school degree, 3 equals some college, 4 equals college degree, 5 equals post-college. So there is an order, but it's hard to talk about the difference between these two as being the same as difference between, say, these two. All right, so ordinal level of measurement, we can arrange the data in order. Next higher level is interval level. So this applies to data that can be arranged in order, but in addition, differences between data values are meaningful. So an example of this would be something like temperatures. If we use degrees Fahrenheit or degrees Celsius, so these can be in order, but the differences between 33 degrees and 34 degrees, it's 1 degrees, right? Fahrenheit or Celsius. So it's that 1 degree difference is the same as the 1 degree differences anywhere on the scale. So incidentally, since we live in Michigan, I looked something up. The highest recorded temperature in Michigan ever, it's going to be in the hundreds. What was it? 112 degrees Fahrenheit. Coldest recorded temperature in Michigan. This one is really cold. Guess what it is? -51 degrees Fahrenheit. So these are in Michigan. I also looked this up just to make it a little more interesting. In the world, hottest ever recorded, 134 degrees Fahrenheit. This was in Death Valley, California. Coldest ever recorded, very cold, -129 degrees Fahrenheit. This was in Antarctica. Okay, so temperatures are kind of an easy example of interval level of measurement. And then ratio, the highest level of measurement of them all is ratio. So this applies to data that can be arranged in order. In addition, both differences between data values and ratios of data values are meaningful. So the ratios, now this is a new one, And we also have what's called a true zero. A true zero. Now in this case, the zero means the none. It means the absence of the variable being measured. So like in the one above, when you have 0 degrees Fahrenheit, it doesn't mean the absence of heat, right? There is still a measurement there. But for the example here, an example we could use would be degree Kelvin. Because in degree Kelvin, when you have 0 degree Kelvin, there's no molecular movement to create heat. So it really is the absence of heat. Or another example would be money. You could have no money at all. You could also have twice as much money. If you have $5 and your friend has $10, your friend has twice as much money as you. So a ratio works. And let's see, what else do we need here? The note here, one of them is the true zero. When you talk about a true zero, it means literally none. The absence of the variable being measured. The other note here is, which we mentioned before, the levels of measurement are often criticized as being inadequate, but are still popular. And here's a little levels of measurement decision tree. So you can start off, and you can see that they start off at the lowest level order. So they go to nominal, and then it works on the way up to ordinal, ratio, or interval. So sometimes this can be helpful. You may not need that though if you just think about what we just talked about and how these come up. And then I'm sure everyone is ready to try another problem, and we've got one here for you. We have got example 5. This is on page 12, and it is number 12. So what you should do is take a couple minutes here, try these out for yourself, and then check back and see how you did. All right, so hopefully you tried these out. It says, categorize these measurements associated with a robotics company according to level, nominal, ordinal, interval, or ratio. So, part A, salesperson's performance. Below average, average, above average. Well, there is an order here, right? There's an ordering here. So it's definitely not nominal. It could be ordinal because there's an order. Also, the difference between below average and average isn't necessarily the same as average. The difference between average and above average. Ratios aren't going to make sense. We can't think of like this divided by that as being a meaningful concept. So basically the data, they can be put in order, and that's about it. So this is going to be ordinal. This is ordinal data. Price of a company's stock. Well, price, we're talking about money. Whenever you talk about money, you've got ratio. This is ratio. Because you can talk about, like we said, the ratios work, differences. You can subtract money and it makes sense. You can make ratios of money, like we talked about. So whenever money is involved, you're talking about a ratio. Names of new products. Well, it's just a name, right? There's not much you can do with a name. So this is just going to be nominal. This is nominal data. Temperature in degrees Fahrenheit in CEO's private office. Well, temperature in degrees Fahrenheit, that's interval, as we talked about. There's not a true zero, so it's not going to be ratio. There's no true zero. Gross income for each of the past 5 years. Again, income would be money. When money is involved, this is going to be a ratio. And color of product packaging. Again, color, it's just a name. That's going to be nominal. All right, so with this, everyone should be all set to go. The key to doing well in this class is to do the homework. So make sure you try the section 1.1 homework and let me know if you have any questions.